Today we're going to go over what different parts of graphs are, critical points, increasing and decreasing, concavity, inflection points, and how we can arrive at those things using derivatives. So first, a critical point. A critical point is where f prime of x is either 0 or undefined. A local maximum is f of p if f of p is greater than or equal to f of x near p. So if I had a graph like this would be a local maximum because near this value, it's the biggest thing around. We'll have a local minimum, f of q, if f of q is the smallest thing near q. So you have that same graph. This would be a local minimum. Now, absolute max and min. An absolute maximum, f of r, if f of r is greater than or equal to f of x for all x in the domain. So if I had a graph like this, we have a local max here. This would be the absolute maximum, which makes an absolute minimum, f of s, if f of s is less than or equal to f of x for all x in the domain. So that would be an absolute minimum. Now we're going to talk about something called the first derivative test. So the first derivative test, if f of x is continuous at c, and c is a critical point. Okay, so if f of x is continuous at c, and c is a critical point, and f prime switches sign from positive to negative, c is a local max. If it goes from increasing to decreasing, we have a local max. On the flip side, if f prime switches from negative to positive, c is going to be a local min. If we go from decreasing to increasing, we have a local min. So this is called the first derivative test. So a tool that we're going to be using is an f prime chart, a chart that will tell us what's happening with the graph. So f prime is our derivative. So it's going to tell me where my graph is increasing and decreasing. So on this graph here, my slope would be 0 at 3. It's decreasing slopes here. So we're going to have negative here and then positive here. Okay, so this is what the graph looks like. But if we didn't have the graph, this chart would give me that information, that if the derivative is negative, my function is decreasing. If my slopes are positive, or my derivative is positive, my graph is increasing, which means we have a local min here. So again, if all I had was the chart to look at, we could tell where our function was decreasing when x is less than 3, because f prime of x is less than 0, it's negative. It's increasing when x is greater than 0 because our derivative is positive. So again, from the chart, we can tell that we have a local minimum at x equals 3 because the f prime switches signs from negative to positive. So as we go through actual AP questions, you'll have a lot of questions like this, and they'll say to justify your answer, this f prime switches sign from negative to positive is our justification. Okay, if we look at the next one, if I made a number line chart for the derivative is going to be 0 at negative 1. It's increasing to that point, and then it's decreasing afterwards. So if we didn't have the graph, we could tell that we were increasing, then it's decreasing, which means this is a maximum. So from the number line chart, we could tell that it's increasing when x is less than negative 1 because f prime is greater than 0. It's decreasing when x is greater than -1 because f prime is less than 0. And then we can tell we have a local maximum, is what that word says there, at x equals -1 because f prime switches signs from positive to negative. This next one, we have a little bit more going on. Okay, so first identifying where my slopes, where my derivative would be 0, are going to be here, here, and here. So -1, 0, and 1. Okay. Then our graph is decreasing here. It's increasing here, decreasing here, and increasing here. Okay, so if I had this information here without the graph, I can tell it's decreasing, increasing, decreasing, increasing, which means I have a minimum here, a maximum here, and a minimum here. So then I could say x equals -1 and x equals 1 are local mins because f prime switches from negative to positive. X equals 0 is a local max from because f prime switches from positive to negative at 0. For D, okay, we have an asymptote here at 0. So I'm actually going to label that as infinity to help me find that. The slopes here are positive. The slopes here are negative. So it is going from increasing to decreasing, but it is not a local maximum because the function is not continuous there. Next, we're going to talk about concavity. We can describe a graph's concavity in two ways. The graph can be considered concave down, or it can be considered concave up. Okay, concave down is going to look like that. Concave up is going to look like that. So here, my slopes are positive, then they're 0, then they're negative. So the slopes are decreasing, which means f prime of x is decreasing. So if we take the derivative of something that's decreasing, that derivative will be negative. So the second derivative is negative. So if the second derivative is negative, the graph is concave down at that point. So we can go negative, make a little sad face. Negative, negative. Concave up, the slopes, so we're negative and then they're getting positive, so the slopes are increasing. Which means f prime of x is increasing. And if we take the derivative of an increasing function, it is positive. So if the second derivative is positive, then we have concave up. So concave up is when we are positive. An inflection point. Inflection points are a point on the graph that has a tangent line and concavity changes. So how can we tell this? If f prime of x switches signs, that means our concavity is changing. So let's look at some chart. Okay, so again, we have the graph in front of us. So we're going to look at the concavity of the graph to determine what the second derivative would look like. This one is concave up the whole time. Okay, so we'd say it's concave up because f double prime of x is greater than 0, and there's no inflection points because it's not switching concavity. Okay, this next one here, we're concave up, and then somewhere here it switches to concave down. I'm just going to kind of estimate that's about right here. Here we're concave down, and then at some point it switches to concave up. I'm going to call it about there. So if I were to do a second derivative number chart, the points where it switches concavity, the second derivative is going to be 0, so at -1 and +1. Then it's concave up for this part of the graph. It's concave down for this part of the graph, and it's concave up for this part of the graph. So now, if we pretend we don't have the graph, and this is what we know, we can tell that the graph is concave up here, concave down here, concave up here. We have an inflection point here, and an inflection point here. So we would say the graph is concave up when x is less than -1 and x is greater than 1 because the second derivative is greater than 0. It's concave down between -1 and 1 because our second derivative is negative. And lastly, we have an inflection point at x equals 1 and x equals -1 because f prime of x switches sign. So similar idea. This one switches concavity. We're concave up to about here, then it's concave down. So for the second derivative, it's going to be positive here, negative here, and then from that, and I'll just label it all on the chart and move on. We're concave up, we're concave down, and we have an inflection point because our concavity switches, our f double prime switches sign. This one, okay, it's concave up, then it's concave down. Let's call it -1/2. Okay, but this is undefined there. Okay, I'm going to just do a big X. So even though my second derivative would be positive here and negative here, it is not an inflection point because there is no tangent line and it's not continuous. And that brings us to the second derivative test. So suppose f of x is a twice differentiable function at x equals x naught. X naught is a critical value of, and f prime equals 0, so it's critical because the derivative is 0. If f prime of x is greater than 0, that means our graph is concave up. If we have a slope of 0 in an area where it's concave up, that is going to be a local minimum. Okay, if f prime of x is 0 and the second derivative is less than 0, so that means it'd be concave down. If we have a point that has a 0 slope in an area that's concave down, that's going to be a relative maximum. So we can make those two conclusions. If the first derivative and the second derivative are negative, the test fails and we have no conclusion. Okay, so let's analyze a function. Okay, so we have f of x equals x to the fourth minus 2x squared. So the first derivative would be 4x cubed minus 4x. The critical values are going to be when this equals 0. I can pull out a 4x, which gives me x squared minus 1. So that's going to be 4x times x plus 1, x minus 1. So the critical values are going to be 0, -1, and +1. To determine whether those are max and mins, we can use the second derivative test. So we'll take the derivative of this, will be 12x squared minus 4. Okay, the values of x that satisfy the hypothesis, which says the critical, that the derivative is 0, are these values, 0, 1, and -1. Okay, so we're going to evaluate each of those in second derivative. So the second derivative of 0, if I plug it in here, 12 times 0 squared minus 4 is -4. The second derivative at 1 is going to be 12 times 1 minus 4, which is 8. The second derivative at -1 Negative 1 squared is 1, so again we have 12 minus 4 is 8. That's enough information for me to determine whether those locations are maximums or minimums. Okay, x equals 0, the first derivative was 0, the second derivative was negative. So f double prime of 0 is a local maximum, and the reason we will state is because f prime of 0 was 0, and f double prime of 0 was less than 0, is negative. Sorry, and this should just say x equals 0, not f of 0. X equals 0 is a local max. So then for our next one, x equals 0 is a local, x equals 1 and x equals negative 1 are local mins because the first derivative is 0 and the second derivative is positive. We'll do one more of these. So we have sine squared. So using the chain rule, our first derivative is going to be 2 sine x cosine x. So my critical values are going to be the things that make this 0 between 0 and pi. So sine of 0 is 0, cosine of pi over 2 is 0, and sine of pi is 0. So those are our critical values. Second derivative, using the product rule, is going to be 2 cosine x plus the derivative of cosine will be a negative, so we'll have negative 2 sine x sine x. So make that cosine squared minus 2 sine squared. Okay, the values that satisfy the hypothesis are the things we just identified. Those are the critical values. Then we're going to identify the second derivative. So f double prime of 0. Okay, cosine of 0 is 1, sine of 0 is 0, so that's just going to be 1 times 2. Pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1, so we're going to have a negative 2. Okay, cosine of pi is 0, sine of pi is negative 1, but we're squaring it so it's positive 1. So that'll be negative 2. Sorry, this one. When we plug in pi, cosine of pi is negative 1 squared times 2. Sine of pi is just 0. So this is just a positive 2. So now, from this information, we can make our determination. So the conclusion, x equals 0 and x equals pi are local mins because the first derivative is 0 and the second derivative is positive. X equals pi over 2 is a local maximum because the first derivative is 0 and the second derivative is negative. All right, so now we have this function, x to the fourth minus 4x cubed plus 2. We are now armed with an arsenal of tools to figure out what's happening with this function, what's happening to this graph without actually having the graph. So first we're going to find our critical points for f of x and the critical points for f prime. So where each of those derivatives are 0. So f prime of x is going to be 4x cubed minus 12x squared. We want to figure out where that is 0. So we will factor out a 4x squared, which leaves me with an x minus 3. So my critical points here are x equals 0 and x equals 3. If I take the second derivative, that's going to be 12x squared minus 24x. Set it equal to 0, factor out a 12x, which gives me 12x and x minus 2. So the critical points for the second derivative are x equals 0 and x equals 2. Next, we want to determine where the function is increasing and decreasing. So we're going to look at the first derivative, and I'm going to break it down. I'm going to actually use this step here. I'm going to use number lines to figure out this information. So I'm going to do a number line for 4x squared. I'm going to do a number line for x minus 3. And I'm going to do a number line for f prime. Okay, so the critical points are 0 and 3. This one's critical point is 3. This one's critical point is 0. So for the first number line, if I plug in a number less than 0, we'll get a positive value. If I plug in a number bigger than 0, I will get a positive value. This one, if I plug in a number less than 3, I'll get negative. Bigger, I will get positive. So in my derivative, we're multiplying a positive number times a negative number. So this will be negative. Positive times negative is negative. Positive times positive is positive. So this graph is decreasing. Then it actually hits a plateau here. Decreasing, then increasing. So this is a plateau. And here we have a minimum because it's going to go down and then up. So this graph is decreasing when x is less than 0 and between 0 and 3, and it's increasing when x is greater than 3. Okay, classify, name any extrema. The only extrema we found was at 3. Okay, is going to be a local min. And when we're asked to justify our answer, our justification is because f prime of x switches signs from negative to positive. Okay, then we're going to determine where the function is concave up and where it is concave down. So we're going to do number line charts for the factors of the second derivative, which were 12x and x minus 2. And I'll do one for f double prime of x. So our critical points here were 0 and 2. So we'll look at these each individually. This one's going to go from negative to positive. This one's going to go from negative to positive. So negative times negative is positive here. Positive times negative, positive times positive. So for my second derivative, that tells me that our graph is concave up, concave down, concave up, and I have an inflection point at those transitions. So from that information, we can determine our graph is concave up when x is less than 0 and x is greater than 2 because it's positive. Second derivative is positive. Concave down between 0 and 2 because our second derivative is negative. The inflection points are at x equals 0 and x equals 2, and our justification is because f double prime of x switches signs. Now we're going to use all that information to graph. Okay, so I just copied this over from the other side. The first derivative was this. It's decreasing, plateau at 0, decreasing, then increasing. So we have a min. Concave up, concave down, concave up. So the three values where something is happening are 0, 2, and 3. So if I plug those into the equation, that's really enough to give me what I need. So f of 0 is 2. F of 2 is negative 14, and f of 3 is negative 25. Okay, so I drew my axes like this. I've got my x-axis. We just have a few points that we care about here. On my y-axis, the 2, the negative 14, and the 25. So my points here, 0 is at 2, 2 is at negative 14, and 3 is at negative 25. Okay, at 0 we have a plateau, so it's going to be concave up and decreasing to get there. It hits a plateau. It's then decreasing but concave down until we get to 2. At 2, it switches to concave up, but it's still decreasing. then it goes to increasing and concave up. So given the number line charts, can we draw our graph? So this is negative, so it's decreasing, increasing, increasing, decreasing. So I have a minimum, a plateau, and a maximum. This one is concave up, concave down, concave up, concave down, with some inflection points. So let's try to make a graph here. Okay, so at -3, 1, 2, 3, we're going to have a minimum. At -1, we're going to have a plateau. And at 3, 1, 2, 3, we're going to have a maximum. At -2, we're going to have an inflection point. So I'm going to label that just kind of halfway in between those two. At 2, we're going to have an inflection point, so between these 2 points. Okay. So we're decreasing and concave up leading into this point. It's concave up, but now increasing to this inflection point. It's increasing concave down to our plateau. Then it's concave up and increasing. Then it's switches to concave down and increasing, and then here we have our maximum. Okay, so for what values of this has a relative minimum? So we want to look at the first derivative. So the fifth minus 24x squared. Okay, I can pull out my least common factor, which is going to be 24x squared. This leaves me with x cubed minus 1. So I'll do a number line for 24x squared and a number line for x cubed minus 1. So my critical points here are 0 and 1. Not -1, because -1 cubed would give me a -2 here. So 0 and 1. This is going to go from positive to positive. This one's going to go from negative to positive, which means our first derivative is going to be negative, negative, positive. So our only relative min, decreasing to increasing, happens at 1. Next problem here, if the graph of x cubed plus ax squared plus bx minus 8 has a point of inflection at 2, 0, what is the value of b? So point of inflection, that's going to occur at the second derivative. So our second derivative is 6x plus 2a. Okay, well, I know that there is an inflection point at the point 2, 0, which means my second derivative is going to be 0 when my x value is 2. So this allows me to find a. Is -6. So I can plug that back into our first derivative equation. Not the first derivative, the original function. So the three things I'm going to plug into this original function are my point, our new a, which is going to leave me with everything but a b variable. So 0 equals 2 cubed minus 6, 2 squared, plus b times 2 minus 8. Yeah. So we get 0 equals 8 minus 24 plus 2b minus 8. So the 8 minus 8's cancel. I'll move the 24 over here. So when I divide, b is 12. Okay. So our last problem. Suppose that f of x, f prime of x, and f double prime are continuous, and has the following things. F is negative from negative infinity to 6 and positive from 6 to infinity. F is increasing until 8, then decreasing to 10, and it's concave down to 10 and concave up after 10. So let's try to sketch a graph here. Okay, 6, 8, 10. Up to 6, our graph is negative, increasing, and concave down. So it's going to switch there, so it's increasing, concave down. It's after that positive, but still increasing and concave down. At 8, it is decreasing, but still concave down. At 10, it is decreasing, concave up, and positive. So it's just going to switch concavity here. Okay, so then the question says, which of the following has the least numerical value? Okay, well, we don't really know what the numbers are, but we have a general sense of, positive or negative. So f prime of 0 is going to be a positive value. F prime of 6 is a positive value. The second derivative at 4, where it's concave down, is going to be negative. The second derivative at 10 is actually 0 because it switches concavity there. And the second derivative of 12 is positive. So we have 3 positive values, a 0, which means this one is our least. That is your introduction to graphing.